So this is the last lecture for this semester. We're going to cover the solution to boundary value problems, which is one class of ordinary differential equations. As we mentioned previously, boundary value problems are differential equations given where a dependent function y, we know its derivative, or we're given a function of its derivative with respect to an independent variable x. And usually this differential equation applies to a particular domain. So applies for particular domain for x, for a particular where x goes from a minimum value to a maximum value. The boundary conditions are usually given in terms of the y itself, and in this case the boundary conditions are called Dirichlet boundary conditions. Or the boundary conditions could also be given as in terms of the derivatives of y. In this case, the boundary conditions are called Newman boundary conditions. There are three main methods for solving boundary value problems. There's the shooting method, there's the finite difference method, and there's weak formulation methods. We are going to cover in this course finite difference method. We're going to just give a brief introduction of how the shooting method, how to implement the shooting method. We're going to cover then the finite difference method. Now the weak formulation methods are more advanced, and they will be covered in a course like finite element analysis, where weak formulation methods are used to solve the differential equation of equilibrium. So first we're going to talk about the shooting method. The shooting method, so let's consider the differential equation. The second derivative of y with respect to x squared is given to as a function of f of x, where we know the boundary conditions are, we need two boundary conditions to solve this equation. We know two boundary conditions. We know the value of y at the beginning, let's call it y0 or y0, and we know the boundary condition of y at the end of the domain. For example, here, we know that y should be equal to y sub l, so we know y0 and know y sub l. I would like to know what the curve looks like, what the value of y is in between. What is y as a function of x? Now, in order to use the shooting method involves converting the function, the differential equation into an initial value problem. Now, if you remember, for initial value problems, the last example when we solved systems of initial value problems, whenever we had a second order differential equation, we converted it into in a system of two equations, where we utilized the initial conditions to solve for the unknown y. Now, in this case, we do not know, we only know y0, but we do not know the initial value for the derivative of y. And so if we would convert this into an initial value problem, we know y0, we would assume a value for the derivative. When we assume a value for the derivative and we solve, then the curve that we obtained would not necessarily, at the end, the value of y would not necessarily be equal to the boundary condition y sub l. Now, the shooting method involves changing the value of s until the numerical solution matches the value of the numerical solution at the end at x is equal to l matches the given boundary condition. The finite difference method is the second method, or the main method that we're going to study in this course. So given a differential equation, a boundary value problem given by this differential equation, the nth derivative of y with respect to x power n, and given as a function, and we're trying to find the value of y, usually this function is applicable on a particular domain. Let's assume that this domain is from x0 to xn, or from point A to point B, we divide the domain into n subintervals, where the step size of each interval is equal to h, x sub I plus 1 minus x sub I. The domain is divided, as I mentioned, into n subintervals, and we label the points as x0, x1, x2, and so on. The finite difference method converts this differential equation into a set of equations to find the values of y0, y1, y2, y3, and so on, all the way up to yn at these specific points in the domain. And this is usually done by converting the differential equation into a difference equation using the numerical differentiation approximations that we presented a few lectures ago. In particular, we usually use the centered finite difference. So we use the centered replace the nth derivative of y with respect to x power n with its centered finite difference approximation, and then we convert this into function of the values of these y's around that particular point. The different boundary conditions can be imposed on the values of yi's. The Dirichlet boundary conditions can be imposed on the values of y, while the Newman boundary conditions, which are boundary conditions on the derivatives of y, can be imposed as additional equations to the differential equation. And we were going to present some examples to show you how this is done. The first example involves solving the heat equation. So we have a rod, and this rod goes from point x equals 0 to the point x equals 10. So the rod has a length of 10 meters. The rod is in an environment where the temperature outside is equal to 20 degrees Celsius. The temperature at one end of the rod is 40 degrees Celsius, and the temperature on the other rod is 200 degrees Celsius. So we'd like to find the temperature throughout the rod in the steady state condition, where the rod is where there's no the temperature no longer changes. And so to do this, first we're going to derive the differential equation that we are going to solve using the finite difference method. First, we need to, the differential equation is written when we introduce, first by introducing the quantity heat flux, where the heat flux is equal to a constant K multiplied by dt by dx. Basically, this quantity states or describes how much heat is transmitted and in which direction. As you can see, the heat flux is equal to a constant K multiplied by dt by dx. Usually, the heat goes from points of high temperature to points of lower temperature, and in these cases, the K is usually for this the K. The constant K is usually a negative value, indicating that the heat flux goes from the positive to the negative. Areas of high temperature to areas of low temperature. Additionally, we're given on the surface of this bar, the heat exits or enters depending on the difference in the temperature between the environment and the rod. And so usually this is done, or the heat the heat is directly proportional to the difference in the temperature, and this constant proportionality is given as the constant B. So we're going to extract a small portion of that bar with a length delta x. The heat going into that bar is equal to K multiplied by dt by dx, where K is given in this problem as negative 10 units. The heat coming out from the other side, using the Taylor theorem, we can assume that Q out is equal to Q in plus dQ in by dx multiplied by dx plus other terms that we are going to ignore. We also are going to assume that there is a heat coming out to the environment. This is equal to B multiplied by the difference in the temperature between the rod and the outside environment, and B in this problem is given as 1, and this is per unit length, which means the total heat is going to be equal to this value multiplied by the total length of this bar, or of this part of the bar, which is equal to delta x. Alright, so heat going in is equal to the heat coming out. We can write this equation, Q in, this is the heat coming in, the heat coming out is equal to Q in plus dQ by dx multiplied by delta x plus B multiplied by the difference in T and the temperature multiplied by delta x. Q in will cancel Q in, delta x after that will cancel with delta x, and we're going to be left with this differential equation that says dQ by dx is equal to negative B multiplied by the difference in the temperature between the bar and the outside environment. dQ by dx, we can replace it with K dt by dx. Therefore, the equation becomes K multiplied by the second derivative of T with respect to x squared is equal to negative B multiplied by T minus the outside temperature. B is given as 1, and we have a value for K given in the problem. Therefore, when we substitute, we get this differential equation. The second derivative of T is equal to 1 over 10 multiplied by T minus 20. You can see this is a second order differential equation with the boundary conditions given in the problem, that when x is 0, the temperature is 40, when x is 10, the temperature is 200. We're actually going to solve this problem twice. The first time, we're going to have this Dirichlet boundary conditions, which is, I just described it, when the temperature, when x is 0, the temperature is 40, when x is 10, the temperature is 200. The second time, we want to solve it with both, with mixed boundary conditions, Newman and Dirichlet. The Dirichlet boundary condition is given at x equals 0, the temperature is 40, but at x equal 10, we're given the rate of change of the temperature with respect to x, or dt by dx, is given as negative 3. So we're going to see how we can solve each of these two problems using the finite difference method. So we're going to start with the first case. We have Dirichlet boundary conditions. We'd like to solve this differential equation using the finite difference method. Again, here's the differential equation. Here are the boundary conditions. And this differential equation can be solved. We can find an exact solution. Here I use the desolve function within Mathematica, and here's the exact solution. Of course, we don't necessarily always have a way to find this exact solution, and that's why we have a numerical solution. But here, because we have an exact solution, we are able to compare this exact solution with the numerical solution that we are going to obtain. So, how to find the numerical solution? We divide the domain into subdomains, and in the problem we asked that the domain be divided into 4 parts. So the domain is divided into 4 parts. The width of each part, or the size of each part, is equal to the total length divided by the number of parts, so 2.5, which means that at the first point I have x naught is 0, x1 is 2.5, x2 is 5, x3 is 7.5, and x4 is equal to 10. So the domain was divided into 4 parts, part 1, part 2, part 3, part 4. The value of x here is 0, the value of x here is 2.5, the value of x here is 5, 7.5, and 10. We know the value of the temperature on this end is 40, and we know the value of the temperature at this end as 200. So 200 is here, and 40 is here, and we're trying to find the temperature in between at these intermediate points. To find the temperature in these intermediate points, this is 1, 2, 3, 3 unknowns. I need to write 3 equations in these 3 unknowns. So to write these 3 equations, I'm going to utilize this differential equation. So I'm going to take this differential equation and turn it into a difference equation and replace the second derivative of t with respect to x squared with functions of these values of the temperature. So basically, I'm going to take this differential equation and apply it 3 times. Apply it here, here, and here. Applying it 3 times will give me 3 equations in 3 unknowns. I will use the centered finite difference. If you look back and open and if you go back and look at the centered finite difference numerical approximation for the second derivative of a function, centered finite difference of the second derivative is given as the following. The centered finite difference at a particular point, let's say x sub I, is equal to the t sub I plus 1 minus 2 t sub I plus 2 sub I minus 1 divided by h squared, where h is the size of the increment. The size of the increment here is equal to 2.5. The differential equation states the second derivative of t is equal to 1 over 10 multiplied by t minus 20. So instead of t, I'm going to replace it with t at that particular point, which is ti. Now, this equation will be written 3 times, when I is equal to 1, when I is equal to 2, and when I is equal to 3. When we this difference equation, we apply it 3 times, I will get 3 different equations in 3 different unknowns. So, when I apply this equation here, ti plus 1 will be equal to t2 minus t21 plus ti minus 1. In that case, I minus 1 is t naught, it's 40. Divided by h squared, h squared in this case is equal to 6.25. This is equal to 1 over 10 multiplied by t1 minus 20. So when we set I is equal to 1, we get this equation. Then set I is equal to 2. When we set I equal to 2 here, this is going to be t2. Sorry, when we set I is equal to 2, this will be t3 minus t2 t sub 2 plus t sub 1 divided by h squared is equal to 1 over 10 multiplied by t sub 2 minus 20. You'll get the second equation. Finally, set I is equal to 3 and we'll get the final equation, and you can see that t4 which appears in the equation, we substituted 200 for t4 because this is the boundary condition given. Now when you look at these 3 equations, these are 3 linear equations in 3 unknowns. The 3 unknowns are t1, t2, and t3. We just have to rearrange them and write them in a matrix form. And as I mentioned, all these methods, all these numerical methods rely on each other. And so once we once we convert it into a matrix form, then we should be using one of the matrix solution techniques that we studied before to find the unknowns t1, t2, and t3. Of course, here we're using software Mathematica. It's very easy to convert to find the solution to these equations just by inverting this matrix or just by using the command linear solve. And when we solve this set of equations, we can find t1, t2, t3 given as these numbers: 43 degrees Celsius, 60.89, and 104.15. All right, so how does this compare to the exact solution? The blue line is the exact solution. The black dots are these values that were obtained. This is, of course, the boundary condition. This is the boundary condition, and the middle ones are the values of these are the values obtained using the numerical solution. You can see that the numerical solution matches really well with the exact solution. So we want to solve this problem again, but instead of using the 2 Dirichlet boundary conditions, we want to now use the Newman boundary condition. Right, before we go ahead with this, just there's a tool on your website where you can change the value of n, which is the number of domains, or the number of sub-intervals, and you can see how the solution is affected. Of course, as n decreases, the accuracy of the method decreases. Alright, so the second, so we're going to solve now the same problem, but given two different boundary conditions. Mixed boundary conditions. The first one is Dirichlet boundary conditions. The temperature here is given. Here we don't know the temperature, but we know the rate of change, or the derivative of the temperature with respect to x. It's given as -3. All right. Okay, so we already have the exact solution. The exact solution is given, or we can find the exact solution using Mathematica, and it's given as this function. So we're going to do a numerical solution and try to compare the numerical solution with this exact solution. So again, with the same number of subintervals, the difference between this problem and the previous boundary conditions is that now we don't know T4. We don't know any of these T's, but we also don't know T4, but we know something about the derivative of T4 with respect to x. Sorry, we know something about the derivative of T with respect to x at this end. So what we know is that the derivative of T at this end is equal to -3, so we're going to, in addition to the three equations that we wrote last time, we're going to add another equation, knowing that the derivative of t at this point is given as -3. So we're going to use the backward finite difference, t4 minus t3 divided by x4 minus x3 equal to -3. So we wrote an extra equation for the extra unknown t4. So we are going to get three equations like before, when setting I is equal to 1, 2, and 3, and then another fourth equation setting the derivative of t4 using the backward finite difference, setting the derivative at t4 to equal to -3. These are the three equations that we obtained before. The difference, of course, in the last time we knew t4 was given in the previous case, but now t4 is an unknown. These are three equations, but four unknowns. I need to add the fourth equation. When I add those three equations, and the fourth equation, and I rearrange, I can form this matrix of unknowns. I can find this matrix form of the problem, and as I mentioned, it's very easy to solve. Find T1, T2, T3, and T4 by inverting this matrix, and we can find the values for these temperatures. Again, if you log on the website, you have a tool that shows the effect of changing the ends, the value of changing the number of subintervals on the accuracy of the solution. You can see here that for 4 intervals, which is what we solved, what we used in the solution. So we've got interval 1, interval 2, interval 3, interval 4. It's not very accurate. It's losing accuracy as we get to the end of the solution. But as we increase the number, we make the intervals narrower. We gain accuracy by doing that. There's another example that I'm not going to go through. You can find it online. Again, the example is given by this differential equation. The second derivative is replaced using the finite difference. The first derivative is also replaced with the finite difference. The boundary conditions are both given as Dirichlet boundary conditions. The u at x equals 0 is given, and u at x equals 3 is given. X, the domain where this equation is applicable, is between 0 and 3. And it's divided into 5 intervals, and you can see it's not very accurate when we compare the exact solution to the numerical solution, but when I increase n, I gain accuracy back. The next example, I will be solving this example because it's an interesting differential equation. This differential equation gives the location y of a cable. So it's given as a differential equation, the second derivative of y with respect to x squared, where x is the length between, or the distance between the two ends of the cable or the chain. This differential equation is given as a function of two constants, usually w, it's the weight of the cable per unit length, and T naught, which is the tension that we desire within the cable. Given those values, we can find a differential equation for y with respect to x. And we solve this differential equation to find the location of the cable. I've posted some links here. This is called, the solution to this equation is called the catenary, or catenary curve. And the detailed derivation is also, I posted the link if you're interested in the detailed derivation of this equation. So here we're given w and T naught as 1. We're given that the length between the two posts is given as 4. And we're given that the displacement at both ends is 0. So here we've got the length of between the two posts as 4. X goes from 0 to 4, and we want to divide it into 5 subintervals. So basically, we'd like to find the location of y in actually 6 points. We're going to divide the domain into 5 subintervals. Therefore, we have 6 points. The exact solution for this, we have an exact solution for this problem. The exact solution is given by this equation. So once we find the solution, we can compare to this exact solution. All right, so we have 5 subintervals implying 6 points. The first point is x sub 0, and the last point is x sub 5. So you can see 1, 2, 3, 4, 5, 6. 6 points. 5 subintervals. The value h, which is the distance between the points, is equal to the total length divided by the number. 4, which is the length, divided by how many intervals. So h, which is the length of the subinterval, is given to as 0.8. So we start at x0, x1 is equal to 0.8, x2 is 1.6, and so on. And for these, we've got 5 values for y that we'd like to find. We know that y here is given as 0, y5 here is given as 0, and we'd like to find y1, y2, y3, and y4. You can count here, we've got 5 subintervals with 6 points. Alright, so to find these 4 unknowns, if you count 1, 2, 3, 4, to find those 4 unknowns, I need to write 4 equations. These are the 4 equations. They're written as, we're going to take this differential equation and convert it into a difference equation by using the finite difference scheme for dy by dx and the second derivative of y. We're going to use the finite difference scheme to replace these with the finite difference equations, and we're going to do this 4 times. When I is 1, when I is 2, when I is 3, when I is 4. So for a general I, the equation looks like this. The second derivative of y with respect to x squared as a function, when I use the finite difference scheme, is given as this equation. yi sub I plus 1 minus 2yi plus yi minus 1 divided by h squared, and h is given as 0.8, is equal to the square root of 1 plus the first derivative of y squared. The first derivative of y squared is given as this. Y sub I plus 1 minus y sub I minus 1 divided by 2h. If you don't remember these formulas, please go back to numerical differentiation to find and look at the centered finite difference approximations for the derivatives. Alright, so we're going to repeat this equation 4 times. We're going to set I as equal to 1, 2, 3, and 4, and write 4 equations. This is when I is equal to 1, I is equal to 2, I is equal to 3, and I is equal to 4. And you can see when I is equal to 1, this value appears in the equation, and we substituted 0 for it. Similarly, when I is equal to 4, this value appeared in the equation, and we substituted 0 for it. And so the boundary conditions are already taken into consideration in these equations. All right, this equation, the set of equations that you see in front of you are nonlinear. So we have to use the Newton-Raphson method, or a method that solves nonlinear equations, to be able to solve them. Here we use the Newton-Raphson method that's built into Mathematica. We just said find root, and we write those 4 equations. We set them and we program them into Mathematica, and we set some initial values for the Newton-Raphson method, and we're able to find the 4 values given as these numbers. When we compare the exact solution given by the blue curve with the black dots, we can see that the finite difference is actually very good for this equation to be able to find the curve, to be able to approximate this curve using those black dots. And again, you have a slider on your website where you can change n and see the effect on the solution. We're going to go through the last example. The last example is this differential equation. It's a linear differential equation, non-homogeneous, because this term x that does not contain the independent variables. The dependent variable y or its derivatives does not appear. So this is a non-homogeneous differential equation. The boundary conditions are given as this: when x is 0, y is 5. When x is 20, y is equal to 8. The domain is between x is 0 and x 20, so I have the length is 20. And we're going to use a subinterval of 2, which means I will have 20 divided by 2. This is 10 points, or sorry, 10 subintervals, meaning I have 11 points. The exact solution can be obtained using Mathematica. Here's the exact solution. We don't need to know how to solve this by hand. This is not the objective of the course. What we're interested in is how to solve this numerically. So for the numerical solution, I've got the width of each subinterval is equal to the length divided by the number. The length is 20, and the number is 10, so 20 by 10 is equal to 2. I have 11 points, starting from x0 all the way to x sub 10. And the value of the x at every point is given. And when this is 0, 2, 4, 6, 8, 10, and so on up to 20. The unknowns are the values of the y's corresponding to every x. But we know the boundary conditions. We know at the beginning y is given, y0 is 5, and at the end, the 10th y, which is the y when x is equal to 20, is given as 8. So these are the 2 boundary conditions. We're going to write, we need to write how many differential equations? We need to write 9 differential equations, 9 difference equations, because we have 9 unknowns. We need 9 equations. We're going to look at this problem and replace the second derivative and the first derivative with their finite difference approximation. The second derivative has this as its finite difference approximation. The first derivative has this as its finite difference approximation. Y stays y and x stays x. And these values are given at y1 and x1. And for I is equal to 2 will be y2 and x2 and so on, depending on the value of I. So we're going to substitute I different values from 1 all the way to 9. So we're going to write this equation 9 times. And when you write it 9 times, we're going to get those 9 equations. The unknowns are the y's, and everything else is given. So we don't know what the values of y's are, except, of course, we know y10. Y10 we substitute to 8 for it, because that's the last y. And the first y, which is y0, was equal to 5, and we substituted 5 for that y. So the boundary conditions are already included in the equations. This can be converted into a set of linear equations that can be solved easily by inverting this matrix, finding these y's, and the solution is easily found. And when we compare the numerical solution to the exact solution, we can find that the finite difference scheme was able to provide a very good approximation to the exact solution. So that finishes our term, and good luck in your final exam.